presentation, I will present to you Lab 4 circuits. So in this lab, we used online software to help us model different types of circuit. We were able to observe and understand how each component of the circuit functions. By recording data such as resistance, voltage, and capacitance, we were able to compare the theoretical circuit against our own calculation of these variables using node rule and loop rule. After we explored how useful node rule and loop rule can be used towards making estimations, in the last part of the problem, we were able to approximate the time constant using data points recorded in this software, which is roughly 6.002 seconds. In the first circuit, as shown below, I predicted the current flow through emitters to be the same using the node rule, and I calculated it to be 0.02041A. Using the online software with the virtual emitter, the result is 0.02, so it's really close. And if I replace one emitter with a voltmeter, the current will stop because there's no complete circuit, and then the voltage across the gap will be the negative of the two batteries. Then I measured the voltage across several points, and since the wire has no resistance in this online lab, the only three places that has voltage difference is across the battery, which is -3 volts, across C and D, and E and F, where the two resistors are, and they add up together to be 0, complying with the loop rule. For any other places, the voltage difference is 0. This is a graph of the voltage change. As you can see, it's basically, as I mentioned, from A to B, and C to D, and E to F. That's the only place it changed. So what if we connected one emitter in parallel with the 100 ohms resistor? Then the emitter will provide an alternative pathway with little to no resistance. So the electrons will like to flow that way, such that I will only really have one resistor working. So the value I calculated is 0.064, close to what the lab is measuring right here. In the second part, we used a RC circuit, and no matter it's charging or discharging, the current is always diminishing. And for a 20 ohms bulb, you can see the time to charge and discharge is around 40 seconds. For 10 ohms, that's around half of it, so it's 20 seconds. So time constant is defined as a product of resistance and capacitance in the circuit, and it is the time which the voltage difference is dropped to 1E of its original value. Using node rule and the loop rule, and looking at the simple circuit on the bottom left, we are able to derive the equation right here. Relationship between voltage, time, and RC, time constant. And if we just plot this part divided by time, we should be able to getting a slope that is -1/RC. And this is what I did, taking 10 data points using the online lab, and I found -1/RC to be -0.16666. And solving for it, I got the time constant to be 0.002. So this is really close to the time constant in the online lab, which will be 0.2 farad times 30 ohms RC, so that will be 6, so it's really close. So discussion question. In real life, if I used emitter, it actually has internal resistance in it, so it reduces the current flowing through the circuit. Same thing with the battery. In the online lab, it charges instantly without resistor if you put a battery and a capacitor. but in real life there's internal resistance in the battery, so it will slow down the charging of the capacitor, so it's different. This is my presentation. Thank you for watching.